Welcome to the spring session of our California Water Colloquium series. It has been going on for a few years now and is gaining momentum, and it looks like people are liking it. The motto of our colloquium is to better educate ourselves so that we can appreciate our precious water. And all of us have a lot to learn, whether we are in the classroom teaching or sitting there as a student or being an activist as a layperson or whatever. We have a lot to learn. And today we have a very genuinely educational topic about California's past climate. And when in the last 100, 150 years, we all had certain impression about water, about its availability for all time. After the talk today, we will get to know that there are some sobering indications that we have to be more careful. Water may be even more precious than what we take it to be. Today, our speaker is what we consider from the area of natural sciences as part of this colloquium series. Professor Scott Stine is a product of this university. He got his PhD here in the late 1980s. And even when he was a student, he played a very active role in what we now call the Mono Lake controversy, but which actually in hindsight is a remarkable success of students with their own point of view, getting interested in the environment and doing something about it. It is a truly extraordinary story. And Scott Stine had the privilege and the pleasure of being part of that when he was a graduate student. After his PhD, he went to Columbia University, and now he is a professor in Cal State Hayward, where he teaches geography and environmental studies. Today, he is going to talk about drought and deluges of California during the past millennium. Scott.
Yeah, and it is a precious resource, and as Nari said, maybe more precious than we tend to think of it. As most folks know, I don't think I need this. I have my very own right here. Good, thanks. As most people know, California started to keep weather records, legitimate weather records, in 1849, and you all know why. Large numbers of Europeans come in at that time. And very quickly after 1849, as these stations multiplied across the state, first in San Francisco and Stockton and Sacramento in 1849, but very quickly in the outlying areas. Monterey gets a station early on, and they spread up and down the valley through the foothills over onto the east side of the Sierra Nevada and out into Nevada, a place that's not California but still very much relevant to understanding California water supplies. As this occurs, we understand very quickly that California is subject to variability, extreme variability year to year and multi-year to multi-year variability in the amount of water that we can count on, or perhaps cannot count on. As early as the 1860s, we discovered wet years. 1861-62 was for the better part of a century thereafter the wettest year on record, remained the wettest year on record for a long, long time at most stations. As it turns out, both 1863 and 1864 were back-to-back very dry years, and we didn't see the likes of that dryness until 1976-77. 1867 and 1868 were back-to-back very wet years again, and people started to realize that California was subject to these big swings. Things stay fairly, let's say they don't reach extremes in terms of individual years, really, until we hit the mid-1920s. And just as we become very relaxed and start to think that California water supply is really pretty dependable, we are hit with what later is called the Dust Bowl. In 1928 to 1934, 6 back-to-back years, averaging about 60 to 70% statewide of our normal precipitation, really turned our heads. Of course, the population of California, human population, was at that time quite low. And in going back through all of the old newspapers, as I had a chance to do when I was still a graduate student here, it became very clear that people were not all that stressed. If something like that were to hit today, it would stress us. And indeed, something like that did hit between 1986 or 1987, I should say, and 1992. We had some 6 back-to-back very dry years there. Actually, statewide, a little bit drier than those Dust Bowl years had been. We've also had some wet intervening years as well, and these cause some stress and some dismay when they come. And like the droughts, everyone is real surprised when they come, and we simply haven't gotten used to the fact yet that these are not abnormalities, they're normalities when we start looking at climate in terms of decades and centuries, and isn't that what climate is? The meteorological conditions averaged out over the decades and the centuries. Well, we're to the point now where we think we have a good sense of California climate, because after all, we've been keeping records in California now for over 150 years. And at some point along the way, we build complacency into this as well. We discover that, gee, with a century and a half of record, we pretty much know what Mother Nature is capable of throwing at us. And we can base a water supply plan for the state of California on what we might call a standard drought, the standard drought being 1928 to 1934, or more recently, our 6-year 1987 to 1992. In amongst those slightly longer droughts are shorter droughts. 1976 and 1977 are back-to-back very dry years in California. And so we tend to look in California at needing to get over a very severe 2-year drought or a moderately severe 6-year drought. And if we can do that, help is on the way, because the next year is going to be wet or normal or some way that will allow us to start to accumulate water. And we'll fill the reservoirs and go on happily ever after. Well, people have worried about this for a long time. Some people have said, aren't we kidding ourselves to think that 150 years is really representative of what nature can throw our way? And so we have, over the years, gone to tree records. And trees, as you know, have a certain longevity. We can go back 300 years in California and find thousands of trees that have over 300 tree rings in them. And we can go back to 400 years ago and 500 years ago, and the numbers start to drop way off at 500 years, but there's still quite a few. And we think, therefore, that we have backed up our 150 years of instrumental record with a very sound paleo record, as we might call it, that is indicative of a much longer and therefore more representative past. The problem with that, as we have learned over the last few decades here, is that the last 500 years is probably the most aberrant 500-year period in the last 8,500 years, temperature-wise, in California. It's the Little Ice Age, and it's a time when temperatures were rather dramatically, surprisingly lower, particularly at night, as it seems to be turning out, than they are today. So by sampling the trees going back 500 years, we think we're sampling the longer, the more representative time, when in fact we're really kidding ourselves. That is anything but representative of what California can throw our way over the multi-centuries time period. I got interested in this when I was doing my dissertation work in the Mono Basin, and while working at Mono Lake, two of my my major professor and two of my signatories are here. Bill Dietrich is here and Ted Oberlander is here, which is a little scary. So they're like checking up on me after all of these years. But I did my work on the fluctuations of Mono Lake, and I'll be saying more about Mono Lake by way of slides in a few minutes. But for now, realize that it's a hydrographically closed lake. It doesn't have an outlet. And so it fluctuates widely, seeking an outlet during wet times and then dropping way down during the dry times. It's subject to big fluctuations in lake level. And so we can use the fluctuation curve of Mono Lake as a proxy for past wet and dry times. And one of the things that I realized fairly early on in working at Mono Lake is that Mono Lake has been low. Mono Lake has subject of this great environmental controversy that turned out pretty nicely, actually, from an environmental point of view. But Mono Lake has actually been lower in the past under natural conditions than Los Angeles made it with 40 years of hardcore water diversions of the streams that would otherwise flow into the lake. Mono Lake has been very low, and that it would seem, point to very dry times in the past. I was able to identify 2 times in the last 1,000 years that Mono Lake was very, very low, and in fact, times when the level of Mono Lake would suggest at least long-term inflow, many decades-long inflow of about 40% of what we would today consider to be normal precipitation. This was a little scary, and I tried to, at least in my own mind, explain this away. Well, it's just Mono Lake. You know, some dark cloud was hanging over Mono Lake and not raining for hundreds of years at a time, but this might not really reflect on the greater California water supply. But as time went on into the mid-'80s and late '80s, I started finding more and more evidence that this was not a local event. This was very, very widespread all over California, indeed all over the western United States. And then I started to find it worldwide as well. And what I'll be talking about here this evening is sort of those discoveries, more or less in the order that I discovered them. What I hope to impress upon people, or depress upon people in a sense, is that we're absolutely kidding ourselves to think that the last 150 years is normal in terms of water supply. As it turns out, as far as I can read it from the Mono Lake record and a number of other records, it appears as though the last 100 years, the last 150 years, is the 3rd wettest century scale period in the last approximately 7,000 years. And we've, of course, built this huge industrial and agricultural and urban infrastructure, all dependent on trapping water in the mountains and then sending it down slowly to the fields and the factories and the people. And we're kidding ourselves in ways that I hope will become clear as we go through the slides. And maybe we can start the slides now. There are some trees, and maybe we could do the lights too. Or not. Actually, some of them are going to need even more darkness. So if we could, yeah, that'd be much better. There, good, thanks. There are some trees in California that do go back more than 500, more than 600 years, and these are the bristlecone pines, and in fact, they are the oldest single-stemmed, at least, living thing on Earth, and we do have a good record out of those that goes back a long, long time. And the next slide shows a 9,000-year-long record let's see, is there a pointer around by chance? Does anybody have a laser? Does anybody have a particle weapon? I should ask with all the engineers in here. Maybe somebody does. I see somebody reaching. I'll point. Great, whoa. Somebody does. Great. Thank you. Thanks. What do I do here? Okay, good. Thanks. You know, he took his house key off of here before he gave it to me. You notice? He's done this before. These are there is 0 BC right there. Here's AD and through here the last couple thousand years, and you can see that there are some low peaks right in that general vicinity. These are the moisture-sensitive tree rings from the White Mountains. And that drought shows up right there. You can see a lot of wetness in through here. Nothing in historical time approaching what we see there within the last millennium. And we'll have a chance to focus in on this as we go along. Next slide. I'm going to take you largely around California and through here, and we'll be looking at Mono Lake, and immediately east of Mono Lake there, Walker Lake, the Owens River and Owens Lake right there, Lake Tahoe right there. I think I put in some slides of the Modoc Plateau in eastern Oregon, but we'll also go eastward to Great Salt Lake area and in fact Yellowstone and some of the areas in the Yellowstone vicinity, and then all the way out into the sand hills of Nebraska. And then we'll go into South America too, but just so got kind of a fix on what we're going to be doing here. Next slide. This is Mono Lake taken on a trip to, I guess I was going to Colorado or something this day. And you can see this great white rim around Mono Lake. The reason for that, of course, is that Los Angeles had for many years prior to my taking this picture been diverting the streams that would normally flow into Mono Lake. And so Mono Lake dropped, and the environmentalists, rightly in my mind, screamed and hollered. And I was out there garnering what evidence I could based on the low lake level. And I could walk around these shorelands that should have been under 9, 10, 11 meters of water, and I was able to walk around and find a whole bunch of things, rooted stumps as you'll see, as well as sedimentary sections that told me what the lake had been doing in the past. Next slide. This is Panem Crater right here. It's just 600 years old. This is an area of very recent volcanism, and you can see that when Panem Crater erupted 600 years ago, it threw out that block avalanche right there, the toe of which is sitting there. This photograph is from 1929, 1930, December of 1929, in fact, in this case. And you can see that Mono Lake is right up against the toe of that block avalanche. Here's Rush Creek, and if you were standing here on Rush Creek today, the water would be right at your feet. It would be flowing by on a very gently sloping plain that is not incised. The next slide is that same area. Here's Panem Crater here. Here's the block avalanche here now. And what happened, of course, is that the lake dropped rather dramatically, and in so doing, not only exposed a lot of shoreland in here that has all these secrets rooted on it and strewn on it in different ways, but it also exposed a nick point that you can see right through there, and that nick point caused the streams, when they did flow, to cascade over the nick point and incise the stream, so that we actually have, or incise the bed, so that we actually have a wall right there that is as much as 10 meters high, with these beautiful sedimentary sequences exposed in it. And those sedimentary sequences, in ways that we'll just touch on here as we go on, those sedimentary sequences very clearly indicate to us how the lake was rising, how it was falling, where it stood at certain times, that can be dated by volcanic eruption, ash layer, as well as radiocarbon dating. Next slide. One of the things that came out, particularly on the deltas, but not just restricted to the deltas, were these stumps rooted in place, 2, 3, 4, 5 right there, 6 right over there, and I now have roughly 250 or so of these stumps that I've found at Mono Lake. Very, very low on the shorelands, and in fact some of these stumps, as you'll see in a moment, are right down very close to the lake itself. I was able to then wade out into the lake when it was at its lowest level and actually find stumps that had not yet come out of the lake. Well, I radiocarbon dated a bunch of these, outermost wood, and was able to group these very nicely, simply into 2 different generations. The first generation was killed in about 830 Cal BP, which is to say about 1120 AD. So you have stumps growing out there that are killed in 1120. How could they have grown? Mono Lake must have been very, very low to allow these stumps to grow. These stumps right here would be under about 30 vertical feet of water were the lake where climate would have it, were Los Angeles not involved in all of this. And of course, we can find stumps right down at the lake margin there as well. So Mono Lake, we might hypothesize at least, must have been real low to allow these trees to grow here. Then Mono Lake, perhaps, let's say, comes up and kills these trees. Well, there's a second generation of trees too, and that second generation of trees is killed in 1350 AD, about 600 cal BP. These are radiocarbon dates. And what this would suggest, at least, is that things got dry, Mono Lake went down, trees were able to grow on the newly exposed shorelands. At about 1120, 1130 AD, the lake rises, kills the first generation of stumps. The lake drops back down again. New trees are able to colonize and grow. And at 1350, the lake rises and kills that second generation. Maybe it's tectonics, maybe something else is going on here, but at least at first I was toying with climate as a conceivably legitimate explanation for this. And to make a long story short, I was able to eliminate the other possibilities that we'll talk about in a little while here. Next slide. Sometimes they show up like this. Mono Lake is renowned for its tufa, and this is a big, thick rind of tufa that formed on the stump. So sometimes we find stumps still encased in tufa. Next slide. Sorry to work you over there. That's going to be the world's worst job. Here's one right down by the lake, and this is not a Jeffrey pine stump or a cottonwood stump, as the others that you saw there are. This one here is a sagebrush stump, Artemisia tridentata, and it too has a covering of tufa on it, and this is right down at the lake, and there are more of these out in the lake. And if we're right here in the hypothesis, our working hypothesis, that it is drought that drew down the lake, then the lake is even lower at the time these things grow because of severe drought, as we're saying here, then Los Angeles made it in its 45 years of hardcore diversions. Next slide. Let's see, let's go on one. That might be out of place. Yeah, here's the Rush Creek here, and you can see that cliff that I was talking about earlier. I'm flying over this now, and exposed in this cliff is this terrific sedimentary sequence of lake transgressive and lake regressive sediments. And we can tell if the lake is rising, we can tell if it's falling, we can tell if it's stabilized. There are soils that form when the lake drops down, exposing a surface that vegetation can then climb onto. A soil forms, the lake rises, it inundates that soil and then buries that soil, so we now have a paleosol. There are stumps perhaps rooted in that soil, and there are ways of dating then these fluctuations. Next slide. Let's Lee Vining Creek, and I did a lot of work along the cliff there as well, and there too. There's the town of Lee Vining, little neon heaven up there. Next slide. This is one of those sedimentary sequences, and hopefully you can see right along here a soil, and it's a little darkened. There's an O horizon right in through there with a layer of humus there, and this thing right here is a stump that was rooted in that soil. Obviously, the soil formed and the stump grew when Mono Lake was low, and then Mono Lake rises. It inundates the soil, kills the vegetation, and then buries that soil in lacustrine sediment there. Here's another root system right over there with the trunk used to come sort of at you, and so it's now gone. Next slide. Another of the many, and I promise to not show too many of these. Can that be tuned in by chance? That looks fuzzy to me, but I've been teaching since 11 o'clock since 8 o'clock this morning. I think it's the little knob just to your, see it on the, yeah, there you go. Ah, that's much better to me. Was that good for you? I'm supposed to say, all right, thanks. These are feet right here, and I was using feet out there because to this day, all the topographic maps, including the newest ones, are all in imperial units rather than metric units. But you can see a dark layer, light layer, a dark layer there, another dark layer up there. These are soils, and in fact, this soil here formed at a time when Mono Lake was not only low, but stayed low for a long time. Then Mono Lake rises, and all of this littoral sand, which is to say beach sand, is deposited on that soil right there. And we have stumps, shrub stumps as well as tree stumps, that are rooted in that soil. And so we're able to date the time that the lake rose and deposited this sand. It dates to about 830 Cal BP, or about 1120, 1130 AD. 600 years ago, in the eruption that created Panem Crater, and I showed you a picture earlier of Panem Crater, there's an ash layer that's deposited. Okay, and this is the ash from the eruption that, amongst other things, produced Panem Crater, and it fell onto a little soil here. After the ash falls, then another little soil starts to form right in through here. The lake rises, buries that soil. A soil forms on top of that now because the lake has dropped down. The lake rises up again, buries that soil. The lake is today low, and this soil here is forming. Now, if you didn't get all those intricacies, it doesn't really matter, because I'm not going to be depending upon those. I just want to show you that we have a phenomenal sedimentary record out there that goes on for thousands of lineal meters, where we can trace these lake fluctuations up and down through time, and date them in a number of different ways, both radiocarbon dating wood, particularly rooted stumps, and with the ash layers, this being the 600-year-old ash, but there's a 1,200-year-old monocraters ash and a 1,600-year-old monocraters ash, and we're a little overdue for a volcanic eruption of the monocraters, as a matter of fact. Next slide. This is the lake fluctuation curve that I was able to put together from all of this, and I simply want to point out that there are a couple very low stands right in here. This should be years Cal BP times 100, rather than just years Cal BP. And you can see here that during the last 1,000 years, there have been a number of low stands. Now, I was able later on to go back and show that this low stand here is actually lower than that low stand there. This turns out to go way, way down here, and I got a lot of documentation on that later on. Next slide. Okay, leaving Mono Lake behind, I've at least hypothesized to you, which is what I was doing to myself, that these low stands of Mono Lake that could be demonstrated based on both sedimentary evidence and the presence of rooted stumps, that is climate driven. Well, I had noticed for a long time that this lake, Tenaya Lake, which is due west of Mono Lake, but now in the mountains on the other side of the crest, on the west side of the Sierra Nevada, at an elevation of about 8150, that this had some peculiar features sticking out of it. Now, unlike Mono Lake, which is hydrographically closed and therefore is subject to these big swings up and down, Tenaya Lake is hydrographically open. It can overflow. So it only goes up so high, and then it throws out all the excess. And then at the end of the year, once all the snow is melted, it drops down, and it might even drop a little bit below its lip at the end of the year. But the next spring, as the snow starts to melt, that lake is up and it's overflowing. And so there's just a very, very narrow range of fluctuations that we can see here, at least during historic time at Tenaya Lake. Next slide. What's your name? Stefan. Stefan, you're doing great, Stefan. I don't envy you. Here's Tenaya Lake, 8149. It says a very, very small basin, most of it bedrock, as you were able to see in that last slide. So not a lot of complications of moisture and regolith that's holding the water back through the year. Every year, virtually all the water comes off, and the next year it starts again from scratch. Next slide. This is what the lake looks like during the spring, a typical spring. It goes way up, and it comes right up to some lodgepole pines and some western white pines there. But even 3 months later, it looks like the next slide, Stefan. That's the basically same place, but notice how the lake has now receded, and the trees are now, instead of being at the water's edge, are a little bit above the water's edge. The following year, even if it's a fairly dry year, the lake will be right up there at the trees again, overflowing, and so on and so forth year after year. In 1976 and 1977, if the park people are correct, and I have every reason to trust them, they're pretty accurate on this, that's the one time that it was dry enough to not get the lake all the way up to here. It rose a little bit in the spring, and then by the end of that second dry year, it was well below its lip. But in 1978, fairly wet year, it's right up to the trees again, and it's doing its normal thing again. Next slide. If you look out into Tenaya Lake, though, you see all of this. Once you get into October and November, the lake has dropped a little bit, and there are the tops of all these trees sticking out of the lake. And so I asked a friend of mine, Phil Caterino, who is about to come out with a book called Diving Sierran Lakes. And he's been down to the bottom of a whole bunch of these Sierran lakes. And he was brought up some great photographs of these. They sure look rooted in place to me, and I'm hard-pressed to explain how they would get down there and be so bolt upright otherwise. But the trees there are rooted in as much as 20 meters or more of water. Now, how do you get these trees to grow? And again, I would stress that we're not talking about what kills these trees. More important, what allows them to grow? How can trees grow in what is today a lake? Well, perhaps it's a drought-induced drawdown of the lake. So I started dating these, and by that time I was hard at work with one of the greatest groups of human beings I've ever known, the people at Lawrence Livermore National Laboratory, and we've been doing a lot of accelerator dating, multiple dates on individual stumps, and lo and behold, there are two generations of stumps here. The first killed about 1120 AD, and the second killed about 1350 AD. Now this lake, even though it's fairly close to Mono Lake, is not hydrographically connected to Mono Lake. They're two independently functioning systems, and the plot starts to firm up a little bit here when you have two independent systems that are showing, both of them, the same two severe aberrant low stands. We continue to do work on this, and we're trying to hone in on the death year and having a lot of fun with it. Next slide. That's not supposed to be there, so let's go on one slide. And that's the one that's supposed to be there, but it has to be tuned in. Yeah. Great, thanks. This is Independence Lake, and I should say that I haven't worked at Independence Lake, but it's very much like Tenaya Lake, and it's about the same size, actually, maybe a little bit bigger than Tenaya Lake. Those of you who have seen Donner Lake have seen a lake very much like this, roughly the same elevation, roughly the same size, the same sort of setting, just east of the Sierran Crest, whereas Tenaya is west of the Sierran Crest. But Susan Lindstrom, an archaeologist who works out of Truckee, California, has been diving in this lake, and she herself has found a number of, is Truckee in Nevada or California? California. Thank you. Keep me straight, guys. I thought I heard a snicker there, and I always feel real self-conscious when that happens. Truckee, California. She has been diving in this lake, and she found stumps rooted in as much as 40 feet of water that date from the second of the two droughts. Now, she hasn't found stumps from the first of the two droughts, but and I feel confident now in calling them droughts, but she's going to keep looking, and we'll see if they turn up. Anyway, the second of the two droughts is represented here in 40 vertical feet of water. Next slide. Yes, sorry. This is a topographic map showing the West Walker River. So we've now bounced around a little bit. We've gone to the west of Mono Lake. Now we're going to the north of Mono Lake. By the way, Independence Lake is up north of Tahoe, so we're really doing a lot of bouncing. This is the West Walker River here, and this is Highway 108, which those of you who drive the Sierran roads will know is the one that takes you over Sonora Pass. So if you come down this road from here, you hit Highway 108 and then reach 395, Highway 395 along the eastern front of the Sierra, the eastern base of the Sierra here, one of the world's really spectacular drives, actually. And here's the West Walker River flowing out of the Sierra, and it hits this canyon and very abruptly turns northward like this, flowing through a very narrow V-shaped canyon, where the stream doesn't have a lot of room to move back and forth laterally. It's pretty well locked in there. Next slide. And as I was driving by there on a very cold November late afternoon in 1987, and it hadn't yet rained that year, and we were already in a drought, so the flow of the West Walker River was really abnormally low at that point. As I drove by, I just saw these stumps sticking out of the river. There's one there, and there's another one there, and there's another one right there, I believe. 3 of them. So I went wading out, and I got some wood from one of the stumps, and that winter we dated it, and it dated to the older of the 2 droughts. Now, we've been dealing with hydrographically closed lakes and hydrographically open lakes. Here's an example now of a river, and right down in the very bottom of this very narrow valley are rooted stumps rooted in place that at this point date from the older of the 2 droughts. Well, that was the last time I got out that year, but the following spring I went out, and the next slide shows, not terribly vividly in this light, what I was able to see. This is an area that I call the graveyard. And am I in your way? I'm sorry if I am. I can. Okay. There's a stump there, another one there, several back there, another one right over here. I was able to find, just scampering up and down this stretch of West Walker River right here, 30 stumps, all of them rooted in place. We dated them. Clearly, both droughts are represented in about equal numbers. And I had about, I think, 35 or something like that at that point. Now, before I go on, I should say something that I probably should have said earlier. These trees don't grow when their roots are fully saturated. Fully saturated is redundant. When their roots are saturated, okay, what happens is that they start photosynthesizing alcohols rather than sugars, and they suffocate or intoxicate, and very quickly, within a matter of a few weeks, are dead. So they can't have their bases entirely inundated during the growing season. So again, here, what in the world are these things doing right there in the lowest part of a V-shaped canyon? Next slide shows what happened in December of 1996. Big flood. Some people say 1,000-year flood, though I think that's dubious, but it was a big flood on the West Walker River, bigger than any flood that the West Walker River had seen previously in historical times, so it's the flood of record. And there was a huge amount of lateral scouring, and what came out was another 100 stumps. So I now have 130 stumps out there, and we're dating away on these. I've taken a GPS, and we have been able to make a map of the distributions of these. You're only seeing the real low ones in here. There's stumps off to the sides on both sides that really confine how big that stream could have been during either of these times that trees were growing down there. And as it turns out, the West Walker River, which is a sizable stream, the 4th largest stream on the eastern side of the Sierra, couldn't have been any bigger than the Little Walker River, which is a minor tributary that comes in just upstream of Chris Flat. I should also say here that I'm always searching when I come upon a new stump site or a new site that is going to say something about fluctuating water levels, either through stumps or the sedimentary evidence or whatever. I'm always cognizant of the fact that there may be another explanation for it. So I try and eliminate all the other explanations. And perhaps what has come to some of the minds in the room here is that, well, there was some piracy event farther upstream that simply deprived the river here of its flow, and therefore flow was diminished, trees could grow. Then the West Walker pirates the water back, and that kills the trees. The problem is this thing is deeply incised all the way to the Sierran crest. There's no way for it to jump out of its bed. So drought becomes really the only plausible explanation here, and the dates of the 2 generations of stumps are the same that we find at these other places here and there. So I started to feel confident in referring to this as a drought. Next slide. Next one. That stream, the West Walker River, continues to flow north and then east, and then it meets the East Walker River, and the combined flow of the West and East Walker Rivers then flows south into Walker Lake. And this is Walker Lake right here. There's Hawthorne, Nevada, not a great spot from the standpoint of beauty. Jim Parsons, who was one of the people who I really admired so much at this university, gave me the soundest piece of advice, as sound a piece of advice as I've ever, as I think I have ever heard. He told me one time, "Scott, never work in an ugly place." And I have tried to follow that to the extent possible. There's beauty to be had out here, but I can tell you it's not in Hawthorne. This is Walker Lake right here, and it's hydrographically closed. And the lake today is about 35 meters below where nature would have it. So it's drawn way, way down, largely because of agricultural diversions in the Smith Valley up and through here. They're pulling water out of the Walker River, and so the lake has been dropping and dropping, much to the consternation and concern of the Indians who live out there, who would like their cutthroat trout fishery to continue to thrive. And it's not thriving at this point. In any case, with the lake that low, I went out and looked for stumps, and indeed there are stumps there. They date at the older of the two droughts, not the younger, haven't found those, but very intriguingly, there's a place right up here where a jet went down in the late 1970s, and the Navy went out scavenging with a hook on a boat for their jet, and latched into what they thought was their jet, because it wouldn't budge, and they sent their divers down the line, and lo and behold, there's a forest down there, rooted in place, a whole bunch of trees that we haven't yet been able to sample. But they're in an additional 60 feet of water, so we're talking about nearly 200 vertical feet below where the lake would be today, but for diversions. And again, this speaks to the severity as well as the length of at least one drought out there, and we'll see how old that forest is when we have a chance. Next slide. Next slide. This is now considerably farther south. It's Owens Lake, and a lake that is much larger than Mono, but not nearly as deep as Mono. And because of Los Angeles's diversions, which started early in the 20th century at in this basin, the lake today is essentially non-existent. There's some water there in the wet years, but for the most part, it doesn't have water on it. It's just a big, huge open playa that kicks up a huge amount of dust. The people at Crocker Nuclear Lab at UC Davis have been working out here, and they feel that confident, at least they did for a while, I assume it's still the case, in saying that something on the order of 9% of the fugitive PM10 dust in all of the United States comes off the bed of Owens Lake here. It's a real problem, and one that the city of Los Angeles, they divert the water, and the state of California, who profits rather handsomely from the lake not being there, because they can go out then and rent out the mineral rights to the evaporite minerals that are exposed, that they are being sued over, and we'll see ultimately what happens here at Owens Lake, still somewhat up in the air. My great good fortune, of course, is that you can now go out onto the bed of Owens Lake and walk around, and when you do, next slide, you find walking down the streams, sections like this, and I won't bother to go into them given the bad light here, but there are buried soils through here, same as what we saw at Mono, and I think the next slide shows that in amongst those buried soils, there's one of them right there, there are rooted vegetation that we can use then as a dating tool to show when the lake in rising inundated the soil, buried the soil, and killed the vegetation. So we have a datable record there from the sedimentary sequences. But in going out onto the lake bed then, next slide, we find stuff like this. This is about a 40-pounder or so. It didn't get out there on its own accord. It was carried out. It has rub marks all over it. It was being used to rub grain by the native people who were there. There's, what do you call it, Mount Whitney. I was out there, a guy said, "Son, which one's Mount Whitley?" I don't know where he's from. Anyway, that's Mount Whitney right there, so you can see sort of where we are. Next slide, some more of what we see out there. These are scattered all over, even the very lowest parts of the Owens bed. And I'm told by some archaeologists who I work with out there that these are of the Rose Spring typology, a type that was made between about 800 AD and about 1350 AD, which fits quite nicely into what we would infer from the other sites, the other drought sites that we have. Next slide. Is a little tufa crust that was on a little stump that was rooted right here, a stump of blackbush. Tetrademia, I think, is the generic name there, and I dated that, and it dates to the oldest of the two droughts. So in fact, when the lake was low, shrubs were growing here and there on the playa. There were certainly spring sites on the playa, and it seems to be at these paleo spring sites where there is paleo vegetation that we find these aggregations of artifacts. Next slide, and the next one. This is Lake Tahoe, and fairly recently now, people working right there at Fallen Leaf Lake, including Phil Caterino, the diver who I mentioned earlier. Phil Caterino has found trees rooted right there now on the floor in about 70 feet of water on the floor of Fallen Leaf Lake, and you guys know the story. It dates at one of the two droughts, and I don't even remember which at this point, but it's more evidence of water levels having been drawn very, very low, far lower than anyone would ever predict from the last 150 years of instrumental record in California. Next slide. This is a place called Osgood Swamp. It's above both Fallen Leaf Lake and Lake Tahoe. It drains into Lake Tahoe, but after a couple hundred meters of fall, so it has its own story to tell, and you can see what it's telling us now. The trees, as at these other modern lakes today, are being kept at bay by a high water table, and trees are not able to get in. These are of course willows here, but scattered out through Osgood Swamp is the occasional tree stump, which I think the next slide shows. Next one. Actually, we'll just hold it here. It doesn't show it because there wasn't a slide there, but that's how busy I was when I was trying to put this together. In any case, it dates at the older of the two generations of stumps, and I put that in simply because it's yet another type of environment. We have hydrographically open lakes, hydrographically closed lakes, streams, and now marshes, all of them, telling us the same story. Things went dry, trees were able to move in, they were then killed by a rise in lake level, only to have the bed re-exposed again through a second drought. Vegetation comes in and is killed a second time. This particular marsh right here is not unlike Osgood Swamp, and you can see it's mountainous there, and there are trunks of trees rooted out there in this marsh. And when I dated them, it dated to the older of the two droughts. But if you walk right out there and around that corner, right through there, you see what the next slide illustrates, which is that. And we're no longer in North America. We're now in South America, and southernmost Patagonia, as a matter of fact. And this is in the area of the Perito Moreno Glacier, where I've been doing some work. And that next slide, I believe, shows the Perito Moreno Glacier, spectacular country. And in fact, this is but one of many places worldwide now where I and others are finding evidence of highly aberrant climate during the same period of time, the period of time that, drawing from the European lexicon, we would call medieval time. People had referred to this for a long time as the medieval warm period, or the medieval optimum, or the little optimum it was called sometimes, that sort of dictates already what conditions were like. So I don't like using that term. I would much rather use medieval climatic anomaly. And what I'm finding, what others are finding all over the world, is that conditions were either abnormally very wet or abnormally very dry, or abnormally very warm or very cool. It was a time when many places in the world exhibited climate conditions, or turned to climate conditions vastly like what had preceded them, and vastly unlike what we have seen during the last 150 years. Next slide. Next one. This is the Grand Tetons now, so we're back in North America, but there's a lake there that many of you have seen and admired. The next slide shows it. It's Jenny Lake, and there it is, and it's spectacular. And who hasn't fallen in love with Jenny Lake when they've been there? But Jenny Lake has trees rooted on the floor of it, and they date at the younger of the two California droughts. The neat thing about them is that I had always wondered whether or not these trees that I was finding in lakes, doesn't work for marshes, doesn't work for rivers, but the trees that I was finding in lakes could have been carried down slope by avalanche, ripped out by the root systems with boulders still entwined, and float out there before they're waterlogged out into the lake, and then sort of turn like this and float down, wanting to cover all my bases. The beauty of that is that this is a windy area. All of the branches of these trees are on the north-facing side of the trees because the south wind trims off all of the growth. That's the living trees. The trees down there underneath the lake have the same orientation to their branches, and there's an eagle's nest in one of them that I can't imagine would have survived the trip down the slope. I mean, maybe, but it just seems to me less and less likely that avalanches or other mass wasting phenomena are behind these trees that we're seeing there. Next slide. And this is now the sand hills of Nebraska, and there too we see evidence of very, very dry conditions having hit Nebraska. How do we see it? Well, the sand hills during the wet times are stabilized by vegetation, and a nice soil forms over the dunes. And then, of course, what happens is that during the dry times you lose the vegetation cover, and these dunes remobilize and start to blow around, and the moving sand buries the soil that had previously formed. This turns out to be this medieval climatic anomaly period, the medieval period, upper medieval period really, turns out to be a time when so much sand blew around in the sandhills here that it actually changed the course of the South Platte River substantially. And so it too, all the way out there on the plains, was a time of real aberration. Next slide. And I'm getting fairly close to done here. You wanted me to go until 5 minutes. Okay, we can do this in 5 minutes. Let's skip that slide. You've seen one sand dune, you've seen them all. Next one. No. Okay, slightly off the subject and slightly later, what happens in the Sierra Nevada and elsewhere on the heels of this medieval period is that within a couple hundred years, we go into very cold conditions. As I had mentioned earlier, this period from roughly 500 years ago to 100 years ago that we call the Little Ice Age. And luckily, we had people like G.K. Gilbert and Israel Russell, the real greats that seem to have really come out of American nowhere to put us on a real sound geological footing luckily in the western United States. They're ours, and we learned so very much from them, and they documented things above and beyond what we would be mindful of documenting today. They went up into the Sierra, and for the sake of posterity, photographed, among other things, the Dana Glacier. And you can see the Dana Glacier here, Dana Cirque, the Bergschrund there. This is the Dana Couloir, where several people have been killed, as I understand it. A friend of mine lost his kneecap there. These are several different moraines here, all three of which date from this Little Ice Age period. Well, this is 1880, And the next slide is 1980, and that's what's left of it right there. Previously, it was all the way over. It was right up against these moraines here. And of course, climate is changing, and it's warming up. And we're coming out of an aberrantly cold period, and we seem to be coming out of it with an unnatural vengeance into something that seems to be aberrantly warm. And we're losing the world's glaciers, which might sort of tug at our emotional heartstrings, but there's obviously more to worry about than that. It's a harbinger of what lies ahead and what does lie ahead. Next slide. That too, the loss of glaciers, is not limited simply to the Sierra Nevada. This too is a worldwide phenomenon, and that's not going to show up terribly well, but that's a glacier that's wasting away in Alaska, and there's a trim line that goes all the way through there, way downstream, where there's very little, if any, vegetation on the slopes. It is wasting back fast enough to expose ground that has yet to be colonized by vegetation. Next slide. Hopefully we'll... this is the exit glacier, and I'm standing down where we believe the glacier was about 100 years or so ago. You can see what remains of it. The next slide, they do a nice job there. Here's where it was in 1927. You can see it in the background. Next slide is where it was in 1978, and of course it's now back there, and it is very much doing what most other glaciers in the world are doing. Now, the remarkable thing here, and the reason that I bring these up, is not only to discuss another kind of record that we have available to us of past conditions, but a remarkable thing is happening as these glaciers in Alaska melt back. As they melt back, what's coming out? Rooted stumps of trees that were sheared off very close to the root system as the glacier came forward. Now, we always assumed that these glaciers in Alaska advanced during the Little Ice Age, starting about 500 or so years ago. As it turns out, though, those trees that are now coming out were sheared off, obviously killed, sheared off during the very time that California was in its droughts. And this goes to explaining one of the peculiarities of our climate system. We have one shot at precipitation during the winter. It's the jet stream, it's the storm track. And if that fails, well, we're sure not going to get it made up during the summer. If it's so dry in California that all of these water bodies are dropping way, way down, where's the jet? Where's the storm track? Well, obviously it's up over Alaska. And this is what we saw getting back to 1976-77. In our two driest years on record in California, Fairbanks, Alaska, and much of Alaska had its wettest winter on record. Ours were the driest years on record. Theirs were the wettest years on record. And it seems to be that analogy that I am most comfortable hanging my hat on at this point. It appears that during medieval time, California saw for prolonged periods of time what we would today consider to be the worst of times. And yet, getting back to something that I said earlier, we've built this infrastructure all on the assumption, the very happy assumption, that it's going to rain tomorrow, which it actually is, but not to undercut myself here, but on the assumption that we have wet years ahead, that the last 150 years is indicative of what we can expect in the future. I'd like to leave you with this thought, really in many ways because of the carbon dioxide loading that's going on as we turn our atmosphere into an artifact. All bets are off as to what we might predict from the past. But even if we were to get the greenhouse problem, as it were, under control rapidly, which doesn't seem to be possible under the present day administration, but maybe in some future administration we'll be able to grapple with this. Even if we were, though, our climate future is not necessarily bright. We can't say that, gee, as long as we get greenhouse under control, everything's going to be fine. Not necessarily fine. We can see times in the past when, under natural conditions, prior to human tampering with the atmosphere, we had climates that would be highly problematical in California today with its large number of people. Well, I'm told that the best is yet to come that the real fun begins when the lights go up again and we take questions, and I'm perfectly willing to do that now. Thank you. Thanks. Thanks a lot.
Would you repeat the question so that we can...
Yeah. Shoot.
You're showing both in stream valleys and in lakes that we have water levels 10, 20, 30, 60 meters less than they are today.
Yeah.
And that's considered a drought.
Well,
You
Yeah.
didn't define the term drought. It has all kinds of meanings.
Okay, yeah.
But at that time, all of a sudden, during those drought times, you have sufficient water to grow forests. And yet we have lots of water coming in now, and there are no forests.
There are no forests largely because the water levels now at these lakes have been drawn down so rapidly that forests have not yet been able to come into low levels. But if you go farther up, you'll see trees that are following that declining lake level down. I take your point, though, and I would answer it. I should have anticipated this. Where do we find these ancient trees? We're finding them at the very lowest places in the landscape. We're finding them in the holes. We're finding them in the declivities. We're finding the forests in the very places that are, in fact, too wet to support forests today that would have stayed wettest during the droughts. And that's, you got a better explanation, I'm perfectly open for it.
You could have had forests up in the mountaintops,
Well, but
they just wouldn't be preserved.
Yeah, the thing is, though, that when we get back beyond 600 years in the tree ring record, it appears as though there's a real drop-off, not just a slackening because of longevity. When we get back to 600 years ago, the number of trees that we have at our disposal drops precipitously. So it does appear as though lots of trees were not able to make it at that time, and were actually up in the mountains were killed by drought. The ones that we see are the ones that were in the very low areas and have now been preserved because they've been wet ever since. They're living, they're in an anaerobic environment, and they'll be there thousands of years from now. We have stumps on the floor of Lake Tahoe that I'm told you can yank a piece of wood off of it, dry it out, throw it above your stove, and you'll smell the resin in it. And these things are in great shape, and they date at 5,000, 6,000, 7,000 years from the floor of Lake Tahoe. So it keeps them in good shape. Yes, Dan?
Two things. I remember years ago you commented on the salinity of Mono Lake and how as it dries out, the water level drops slower and slower as the salinity keeps increasing, evaporation declines. I was wondering if there's any implications of that. And my other question had to do with the work of Spencer Woods and whether or not his results correlated with what you found.
Spencer Wood from University of Idaho worked on the Mono craters, and he was the first to date the Mono craters' ashes, and we have a lot of good information from Spencer. He was dealing with much longer periods of time. He was dealing with sort of thousands of year-long climatic conditions rather than with the century-scale climatic fluctuations.
I was actually thinking of his work on the meadows in Yosemite.
Yeah, those are the ones. That's the one. So they're not really comparable. He and I, though, co-led a Friends of the Pleistocene trip in 1984. Ted Oberlander was on that, too. Your other question, though, about the salinity of Mono Lake, without being terribly long-winded here, that's a joke, isn't it? The lake, as it drops, does indeed get more saline. Saline water doesn't evaporate as rapidly as fresh water does. So for that reason, and because you have a smaller and smaller surface area as the lake drops, you lose less and less water every year as the lake is falling. Sure. So it slows way down in its descent. It's tougher to get that lake to drop from 6,380 to 6,370 than it is to get it to drop from 6,400 to 6,390, put it that way, for both of those reasons. Yes?
Have you seen any correlation between the Mayan civilization, decline of Mayan civilization in your drought years?
Yeah, in fact, there's a great paper by, was it Kennett? I don't remember, in Nature, June of 1995, I believe it was, where he shows that the decline of the classical Maya, which occurs, I think it's right around 900 AD, which is just when the California droughts are really starting to kick in here, that classical, the demise of the classical Maya on the Yucatan Peninsula coincides with the driest time on the Yucatan that he can find in 7,000 years. Did it cause the demise? There are lots of people out there who think that climate has nothing to do with the demise of civilizations. It's the workers going on strike, or it's nothing. And so this is very, very controversial. But I mean, I think the smart money is that these people all of a sudden had a hell of a time. That happened in California as well. There are some people living along the coast of California down by Santa Barbara and on Callegas Creek. And a friend of mine, Mark Robb, wrote a really wonderful monograph on this. He was able to show that the people who were living there thrived prior to the first of the California droughts. And they were big-boned. He exhumed the skeletons, obviously. Big-boned. He does trace element analysis on the hair, and they have all the essential nutrients and everything. And they're being buried with trinketry from all over California and the western United States. The droughts hit, and all of a sudden the people are being buried younger, they're smaller boned, they're malnourished, and they have lesions on their bones that I'm told are an indication of a malnutrition-induced immunodeficiency problem. And instead of being buried with jewelry, they're being buried with crushed skulls and war wounds. And it does appear as though there was at least a coincidence between what we would call today severe conditions and these people having a tough time of it all of a sudden. Anasazi, likewise, though that's a little more complicated. But the Tiwanaku at Lake Titicaca, very similar story. They seem to take a dive just as California goes into its droughts. And I wish we had time to talk about that. Yes?
You haven't mentioned trying to measure the age of some of these trees to try to estimate how long these droughts.
I sure should have mentioned that. You're absolutely right. The first generation of trees, the older of the two generations, has as many as 200 growth rings in them, indicating that the drought has to have continued for roughly 200 years. The second of the two droughts, the trees are smaller. 140 rings is the biggest I can find, or is the oldest, excuse me, the longest lived, I should say, that I can find. But I do believe that was the more severe of the droughts. I think that what I'm seeing at Mono Lake and some of these other lakes is the lake having gone down and more or less stabilized and trees growing. I think Mono Lake was still on the way down when the second of those droughts broke. It didn't reach the low stand that it would have had the drought continued. But yeah, so these were long-lived. Yeah, makes it seem all the less plausible, doesn't it? Though there's just site after site after site, and they all date the same, and there's two generations, and there are different kinds of indicators, and so yes.
The comments on civilizations, do they also extend to the Peruvian and Chilean Western civilizations that declined?
I don't know. I can't say. Maybe someone else would like to comment on that. I don't know about that at all. Yes.
Do you have enough data to put any cyclic pattern to these droughts and causes to them?
I can't talk about cyclicity, because these were rare events. You can find them other places in the record, but we haven't seen anything like it since. In terms of what was the other question? I'm sorry, I've been talking since. Oh, the causes. Well, jet stream and storm track being to the north of us, but what causes that? All I can tell you at this point, and this doesn't make a lot of people happy, is that every time there's the century scale sunspot maximum, Mono Lake is low during the past few thousand years. Every time there's a century scale sunspot minimum, Mono Lake is high. And this is not the 11-year sunspot cycle now, but the Maunder minimum, the Sporer minimum, the Wolf minimum, the medieval maximum, the Roman maximum, there are all these identifiable sunspot aberrations that we can find, both from the observational record, from the astronomical record. John Eddy looked at this a couple decades ago now, but once he was able to show from the Chinese record and from the Italian record that people had observed aberrations in sunspots, very quickly Minzy Stiver at the University of Washington, the Quaternary Research Center, and other people started looking at the radiocarbon signal of this, and we can now go back and look at the fluctuations of radiocarbon production year to year or group of years to group of years in the trees and see when the sun was active, when the sun was inactive. When the sun is active, Mono Lake is low. When the sun is inactive, Mono Lake is high. Is that a coincidence? Maybe. And maybe volcanic ash, aerosol forcing comes in here. I really don't know. And that's a little bit beyond where I've been able to take this, but there's a lot of interest in it. Yes?
Is there any evidence that there was a forward shift in the jet stream in the southern hemisphere as well?
Yes, and that in fact is why Patagonia, southern Patagonia, is dry. It's a little odd. Patagonia is dry largely because of the Andes. But Patagonia is real dry if you strengthen the westerlies over the Andes and you get that subsidence, that rain shadow effect on the east side of the Andes. When the jet stream is farther, in the southern hemisphere is farther equatorward, Patagonia is actually wet. The jet stream isn't over Patagonia, but Atlantic moisture can get in there and get Patagonia wet. Patagonia gets dry when the jet stream is right over it. Now that's the exact opposite of what happens in California. California is wet when the jet stream is over it, dry when the jet stream isn't over it. Exact opposite, and that's because Patagonia is 50 degrees south latitude. We are here 37.5 degrees north latitude, so they're not exactly comparable latitudes, and I wish we had another hour to talk about that. I could show you on maps. It really works out really beautifully with the synoptic meteorology.
Okay, Claire, you have
Well, I was going to ask, getting back to the timing of things, is there a good explanation for why a dead tree lasted for 200 years or so as the second generation trees were able to grow?
Yeah, there's a really neat explanation, and if I had brought those slides, I could probably convince you of it. Let me try without the slides. If you go out to those trees, even the mono trees today, what you'll see is a rather barren plain of Disticlus spicata, which is a dryland grass that grows in rhizomes and can tolerate a lot of salt. But right up next to the stumps, growing in a circle around the stumps, is rather luxuriant Juncus balticus and other graminoid vegetation that requires a fair amount of moisture. And clearly what's happening is that these rather deep-rooted trees continue to wick water up to the surface, and they're supporting water-loving plants all around them. And if you go up to these stumps, most months of the year, they're wet. Despite the fact that they're on these dry shorelands, they continue to wick water. Now, they do dry out ultimately every year, as I've seen it, and they are, in fact, now decaying. I've noticed decay in the couple decades that I've been working out there, so they're not going to last forever.
They're actually 60 feet high, maybe, and it just seems unlikely that dead tree is going to last a couple hundred years.
All I can tell you is that the 900 or 830 Cal BP trees at Tenaya Lake are in really crappy shape. The 600-year-old trees still have the bark on them. So I don't know if that's convincing or not, but it's one of the observations we've been able to make.
I have one question.
When the lakes fell and the forest started coming in the Mono Basin there, that forest was coming in on highly alkaline saline soil, right? Would it take a while to flush that before the Jeffrey pine could get going there? And would that make the Mono Basin trees Would that put a little lag in the record for Mono compared to others?
It might, except that we can go to other places in the Mono Basin and see evidence that would not support that. If you go to places in the Mono Basin that aren't deltas, and all the stuff that I was showing you in the Mono Basin is deltas, it's coarse sand and gravels, fist-sized, in some cases skull-sized gravels that are really pretty easily flushed. If you go other places in the Mono Basin, what you find are very tight sediments, silts, that are not as easily flushed of the soluble minerals. There, on those very fine-grained substrates, you can see the 3,500-year-old high stand of Mono Lake as a vegetation line. It's had 3,500 years to be leached of the solubles, but the stuff above that line, where the lake hasn't been in many thousands of years, 10,000 years or more, above, that is vegetation that can tolerate, vegetation that cannot tolerate the saline soils. Immediately below that 3,500-year-old shoreline, all you find is vegetation whose nitrogen symbionts can't tolerate the saline soil. So there, I would say that there's a real lag. Paleobotanists, I understand, call that echosis time, the time that is required to prepare the substrate for something to come in and colonize it. On the deltas, though, you don't see any pattern like that at all, and I think it's because there's a lot of water there. Even in the dry years, there's still some stream flow that's moving over that, and those are very easily flushed soils. So, yes?
I wonder if you could comment a bit on the longer time frame that you mentioned. You compare these events to 7,000 or 8,000 years of record. I wonder if you could talk about what methods you use for that time period, specifically how well do those methods corroborate the droughts that you do see preserved?
How well do they corroborate it? Well,
pollen cores.
Pollen is a little tough because there's a lot of echosis time involved in a pollen core, and that's more recording the sort of 1,000-year swings back and forth. There are some palynologists out there who are very successfully looking year to year in varve sediments, and they have maybe a 10-year resolution, but those kinds of records are rare. Where we do have those kinds of records, for example, Peter Wigand, who used to be at University of Nevada, the Desert Research Center, and I'm not sure where he is today, but he has lakes. Diamond Pond is the one that I remember in eastern Oregon, and he has a record that goes back 7,000 plus years, and the driest time he can find is the medieval period, based on his pollen from that 7,000-year record at Diamond Pond. Somebody help me out. He's at Davis. Great guy. God, why can't I remember his name? Because I'm going dead here. Owen Davis, thank you. Owen Davis has a record from Los Angeles, from down in the marshes of Los Angeles, and he has a record that goes back many thousands of years, and he says, too, that the driest time he can find, apparently sagebrush, artemisia, if I remember correctly, comes in down there. The driest time he can find down there is approaching and into this medieval climatic anomaly. Now, there are other records that go back that far, but they're largely lake fluctuation records. And Owens Lake is one of them. And all I can tell you is that in those records, they also find desiccation events other than these two that I've been talking about, where Owens Lake lost all its water, but they also find these medieval events as well. So, I'm sorry, what?
Lynn Ingram stuff in San Francisco Bay, I can't remember the dates on that.
Lynn Ingram stuff shows this. The only reason I hesitate to bring up her stuff, which I think is really remarkable work, but Lynn would be the first to tell you. Is Lynn here? I'll let her tell you. No, Lynn would be the first to tell you that we don't have great dates on that, because the upwelling off the coast of California changes through time, and that's putting a whole new layer of confusion into dating of shells. She seems to think that it's dry during this time, but the dating could be one side or the other of these medieval droughts. Dan.
Going back to Ted's question, my question is, in the short period that the lake was drawn down, well, not drawn, but lower due to the diversions, did you notice any pioneering of trees into the delta soil?
Oh yeah. Down on the bed itself, lots of willow, now cottonwood, and a few Jeffrey pines are coming in. You know, one of the things that I did in worrying about this echosis time was to just walk around the bed of the West Walker River and the bed of Mono Lake and whatnot, seeing how available seeds were. Well, I had a class out there, and we all joined hands and went down the bed of the nearly dry West Walker River in September, and after taking maybe 30 steps or something like that, we had 800 pine cones. So they're everywhere. They're just ready to go, waiting to go. And yes, trees are coming in at Mono now that the lake is low, despite the fact that there have been many, many years of no stream flow, which I don't think nature would have done. Nature wouldn't have ever, I don't think, completely dried out those streams, but Los Angeles can. So, if that's...
I have
okay.
The entire explanation we have here is what happens to a jet stream on the storm track on the west coast of this North and South America. But because the Earth is a conservative system, there is something very dry in this water some other place.
I'm sorry.
The Earth is a conservative system.
Sure.
Is there any evidence from Australia or some other place, not along the west coast of the New World, where we have excess precipitation during this time? From a global point of view.
I can tell you that other places were dry during this time. Same period. Angkor Wat, you know, the great facades and temples and statues. I went into a bookstore. I should never go into a bookstore with a wallet on me. Walked into this bookstore and there was this beautiful book there, a big picture book on Angkor Wat, and I opened it, and the very first sentence was, Angkor Wat was all about water. And it declined, and I think it was 900 AD or something like that. And there are more and more of these places that are coming up. Whether or not there was drought that drove those people down, we can't say. All we can say is that people declined there. It was all about water, and they were, I don't know, I'm talking through my hat at this point because I've never been to Angkor Wat, and I understand that it's mined so heavily that I shouldn't go to Angkor Wat. Oh.
To follow up on Aaron's question, in Europe and Asia during this time, there were lots of people writing about many things. I wonder if there are written records that would give evidence to correlate the changes in the climates in those areas.
Yeah, and I should have I forgot about Europe. This medieval period was aberrant in Northern Europe as well, and that's in fact where this was first called the medieval warm period. Grapes were being grown in England, and many of you know this story. You can go there today in central England and see on the slopes the ghosts of terraces that were being used during the Middle Ages to grow grapes. Only during the last 5 or 6 years, as I understand it, have grapes now started to be grown in England again. Has England become warm enough to start to grow grapes? But grapes were being grown there. The various erics were in Greenland and Iceland. Greenland was being occupied, colonized. There's good evidence that things were warmer at this time, though there in Europe, the signal is much more strongly temperature rather than precipitation. Here in the Americas, at least in the Western Americas, it's much more precipitation than temperature. Grace Brush at Johns Hopkins University, who also works with pollen, has been in contact with me and I with her on this. She now has a core from Chesapeake Bay, and pollen core from Chesapeake Bay, and I think it was covering 3,000 years or something like that, but she sees drought at Chesapeake Bay during this same period of time. So, from lots of different places.
Weird point, that same time period was the expansion of plagues.
Was the expansion of plagues, yeah, and people like H.H. Lamb and others have tried to tie that into to the higher survival rate at higher latitudes of fleas. And people are starting to write about this now, too, that as the world warms now, does that redistribute diseases? Well, I would think that it would. I mean, these things are temperature dependent, so hang on to your hats. It's only going to get worse. We've lived through the best of times, and it's going to get worse.
Yeah, I was just thinking, I'm on the Public Advisory Committee for the State Water Plan, and this year's update, I guess, is the first one to take into account climate change at all. Did you see any evidence of snowpack changes?
I can't see evidence of snowpack changes, except that snowpack is going to be reflected in runoff, and these various records that I've been talking about are a function of runoff. But I can't say anything about snowpack. Yeah. Okay, my pleasure. Thank you very much. Good.